back. Um, so from talking to a number of you last time, I think it's clear it's worth doing the following example altogether. I'll leave bits of it as an exercise, but let's work on A2 with the coordinates x and y, p and q. A4, thank you. So last time we talked about O of x equals 0 on A2 with coordinates x and p. Right, so it was here. And W equals px, and we said this was the sort of fiber-wise model for Knurr periodicity for a divisor. I think it's worth doing rank one more because you can feel like you're not doing anything when you're just doing p times x. So let's let W equals xy, or xp plus yq. And what we did was we calculated endomorphisms of this thing as a matrix factor, of this Sheafy matrix factorization. We saw that it was an exceptional object. So I want to do that here. I think it'll be illustrative, and then I'm going to use it to talk about Knurr, to do a nice proof of Knurr periodicity. So on like this, right? So what's the classical viewpoint? And we're going to have L is going to be the set x equals y equals 0 in A4, and Q is just going to be the set W equals 0 in A4. So I'll draw it's this picture only one dimension up. So I guess I should really draw for you a quadric in P3 and then the cone over it, and then a line on the quadric giving you the linear space on the cone, whichever picture you like better. So these are both lies in different ways because I'm in A4. So it's the classical story of how we get. I want to show you a little bit how this sort of Eisenbud style take a free resolution and do a null homotopy turns into the style that we've been doing. So you take we take the resolution of OL on A4 is just a Koszul resolution that you've seen many times now. X and Y here. Minus Y and X there. And the point is that if I draw the same thing twice, put this down below. I'm going to put a bunch of stuff in the middle. Minus Y and X. Right, so we said that the map W here is 0. And so if I put W here, it's null homotopic. And so I can choose a null homotopy. And in fact, there's a preferred one. The preferred one is, I should put PQ there and minus Q P there. So if this is D and H is there, then DH plus HD is W. And also, H squared is 0, right? So we don't, this issue about needing to mess with H, H squared being null homotopic and you have to choose a thing to, right? Here we don't have that. H squared is just 0. This times that is 0. Yes? This is all on A4. This is. Yeah, well, no, yes, sorry. I'm saying that that was a slightly silly thing to say. I was saying that this complex, this complex is quasi-isomorphic to that, which, yeah, you're right. That's a misleading way to write it. Right, so how do we get the resolution of OL and the matrix factorization? Again, to show you something you've seen many times now, OL comes from O, well, from OQ, if you like, from OQ squared. This is X and Y. Comes from OQ squared. This is this thing that we always write, Y minus X, P and Q. And this is, if I've done it right, this is DH plus HD. Right, it's this O plus that O, and this is DH plus HD. In an appropriate sense, and here we get P. Thank you. It's worth getting this right. So this will be Q, Y, X, minus P, and so on. And then it repeats. Right, so that was the classical story. And what does this have to do now with our story? So let's let X and Y have R charge 0, and P and Q have R charge 2. Right, so now W has R charge 2. And I claim that the matrix factorization OA4 squared, let's give these matrices names. Let's call this one M. Right, so M is going to be YQ minus XP. If I do this matrix factorization, OA4 squared MN. So I claim that this is isomorphic to just O of OL back and forth to 0. So I leave it to you to put the right shifts in here, right? Right. So my matrix factorization, I have E is O to the 4th with appropriate R charges. So that if I take D to be M and N, this will go from E to E shifted by 1. Right, so you need some shifts on these because you remember P and Q are sections of O of 2, whereas X and Y are sections of O. So exercise, figure out what those appropriate R charges are. So I claim that those are isomorphic. These are isomorphic in this derived category of A4 with W. So that means the category of matrix factorizations up to homotopy and invert quasi-isomorphisms. So I want to do that with two exact sequences. One is the ideal sheaf of L in Q goes to OQ, goes to OL. So this is an exact sequence. either of, so this is an exact sequence of sheaves on A4 or on Q, or of matrix factor, or of, curved DG sheaves with D equals 0. All right, and that's all right because, the W times the identity on OQ is the same as 0 times the identity on OQ. But the Sheafy matrix factor, but OQ is, so we're going to do that to compare OL to that. And then we're going to do something else to compare this ideal sheaf to this matrix factorization. But OQ is 0 in the derived category, in the category of matrix factorizations here, as follows. I can write OQ comes from O via W. Down here I'm going to have O via 1 to O. And then let's see, I think I want to put 1 going up and W going down. And here I want to put W going up and 1 going down. And if I haven't screwed up too badly, that commutes. Right? So now this is a short exact sequence of curved DG sheaves. Or these two are matrix factorizations with D is coming like that. Right? And that one's a curved DG sheaf with D equals 0. But these two, right? So when we go into the derived category, this will become an exact triangle, right? Because it'll be the totalization of some exact sequence. But these two here are contractible. As we saw yesterday, we wrote down the homotopy between 1 and 0. So this is isomorphic to 0. So these two are already 0 in the homotopy category. This is the cone on that map, or it's quasi-isomorphic to the cone. Like we set up quasi-isomorphism so that would be the cone on that. And so this becomes 0. So the ideal of L and Q is, how about this? So OL is like that in the category of matrix factorizations as Sheafy matrix factorizations. On the other hand, we could do this. We have the ideal of L in Q we've seen is resolved by O A4 with the matrix M here. And so that's an exact sequence of sheaves on A4. The kernel of that is the image of that. Maybe I'll stick the zeros here for emphasis. And this can go back and forth with 0. This can go back and forth with OA4. So here I want to put N going down and M going up. Here I want to put W going down and 1 going up. Thank you. Thank you. Yes, they should. Right. So this is contractible. So these become isomorphic in the derived category of A4 W after we kill off totalizations of. If we kill off the totalization of this thing, then this becomes the cone on that map. So this map becomes an isomorphism. Great. So that's how you do a free resolution of OL. How you replace OL in the category of matrix factorizations with the matrix factorization that it's meant to correspond to, right? Which is M, N, M. So now let's compute. Sorry, questions? So I have not put in any of the brackets that I should, and I invite you to do that, especially there. So now let's compute RHOM from OL to OL in the category of matrix factorizations. Right. So this thing was E. Was also there. So this is going to be RHOM from E shifted by 1 to OL. Right? Because E was IL. I guess I need a minus 1, don't I? So I just take, so this is R gamma of E dual shifted by 1 tensor OL. I don't have to derive the tensor because this is a thing of vector bundles, right? So this is just R gamma of E dual shifted by 1 restricted to L. And you notice that M restricted to L is this matrix. It's just 0, P, 0, Q. And N restricted to L is Q minus P, 0, 0. So if you want an exercise, so you unwind the shifts to find that E dual shifted by 1 restricted to L is the Koszul complex OL, OL squared, OL. Here I'm going to have P and Q, and here I'm going to have minus Q and P. Or, well, probably it's this one, isn't it? Well, maybe it's, and this is quasi-isomorphic. Now we're just talking about good old complexes. This is quasi-isomorphic to O of x equals y equals p equals q equals 0. The origin. This is a skyscraper. Skyscraper. At the origin. So R gamma of it is just K. Yes?
I mean, you're on A4, so R gamma is just gamma anyway.
Yes. Yes, indeed. Right. Yeah, we said if we were on an affine space, we were extra happy. Okay. So if you like, put all the shifts back in and see that this curved DG sheaf now supported in the locus where W equals 0, so I can split it into graded pieces is really that Koszul complex. All right, so this is interesting, right? This before, when we were looking at this picture in A2, you might have got the idea that this matrix factorization was rigid, right? It had no x1 with itself. It had no deformations because this line couldn't move inside of W equals 0. But here, this plane in this quadric in A4 can absolutely move. Right? I can move this line on this quadric surface. And so I can move the plane over it in the cone over it. And yet, the matrix factorization doesn't change. So this is some incarnation of the calculation you did with that syzygy bundle earlier, although in lower dimensions. I guess already when you deform L, OL moves, but IL doesn't move. Okay, questions about that? If it starts to feel like we've done the same example over and over and over, it's because all the other examples are too messy. Like the 3x3 one I thought about trying to find the self-exits of that and see that it was, like the cohomology of O on an elliptic curve, and it just doesn't work in public. Okay, so now we wanted to talk about Canara periodicity. And you recall the statement was I had some y in x cut out by a section S of a vector bundle E with rank of E is codimension of y in x, so a regular section. Sometimes people call this transverse, but we're not actually asserting that y is smooth. Maybe you can imagine at a first pass that y is smooth and S is transverse. Then the functor d of y to matrix factorizations of the total space of E dual S, where we give the fibers have R charge 2 and the base has R charge 0. I stated this yesterday. I'm stating it again. And S we can think of as a section of E or as a function on E dual. And the map is the one that I drew last time. This is an isomorphism. And Ed is going to use this a bunch later. So last time I stated it only for a line bundle. It works in this generality. The difference between the line bundle case and the general case is just a bunch more indices. So I'm going to prove it in the line bundle case. So I'm going to prove it for y is the origin inside of x, which is a1. So let me just say to go from here to an arbitrary divisor, it'll be the same algebra. And if we want to go to higher codimension, well, I guess if it was a complete intersection, if E was a sum of line bundles, you could induct probably. To higher codimension, it's the same ideas and more notation. So as I go through the proof, I'll indicate how this goes. So we have two functors, one from the derived category of a point to the derived category of A2 with W equals Px. So this was the x direction. This is the p direction. So here's A2, thought of as the total space of a vector bundle over A1. And the map sends O of the point to O of x equals 0. Let's call that, I don't know, phi. And then the functor back the other way, maybe we call it psi, which is the left or right adjoint of phi, if I've done things right, is going to send some E to global sections of HOM from O. Let me not call this E. Let me call this F, because I want to use E for the special one. From O of the point to F. Yes. Yes, thank you. Thank you. O of x equals 0. In general, what's the general story? We had the total space of E dual mapping to X. We have the total space of E dual restricted to Y mapping down to Y. Right. In general, the functor phi will be I star pi star like. It will be pull up and include. Remember, because the derived category of a point, everything is just a sum of, direct sum of shifts of this thing. Right, so this tells you everything you need to know. And coming back the other way, I think this is I believe this is the right adjoint. Going back the other way will be sort of, this is either, maybe this is I upper shriek. and then pi lower star. Now you might say, I have no idea how to push forward a matrix factorization. And you're quite right. Here the superpotential is 0 when you restrict there. But this map is not proper, so you have to worry quite a bit about whether you're going to take something sort of finite and coherent down to something unbounded or quasi-coherent or whatever. I guess not unbounded, but quasi-coherent. And the issue is that there's a whole theory of this kind of thing that I don't want to get into. What you need is that the critical locus of your superpotential here, if I wanted to push down, needs to be proper over x. The critical locus where the second derivative vanishes. So I want to show that these two compositions are the identity. So I want to show that psi after phi of O of a point, this is R gamma of O x of Hom from O x equals 0 to itself. You can see I'm doing something slightly annoying. This psi actually takes values in the category of complexes of vector spaces, doesn't it? This is in the derived category of C vector spaces, which is the same as that. I hope you don't mind my identifying these two. This is just C in degree 0 from yesterday. Right, so the calculation, right, we've seen this before, that an exceptional object, right, O of x equals 0, our favorite, O of this thing, is an exceptional object in this category, which is the same thing as a fully faithful functor from the derived category of a point. So I've checked that this is fully faithful, and now the thing is to check that the other way is fully faithful. So for psi after phi, phi after psi, this is going to go from d of a to w to itself. So I claim, right, this is the functor is f goes to R Hom from O of x equals 0 to f tensor O of x equals 0. And so what I want to say, and this is a bit of a stretch, but maybe not such a stretch. So there exists a theory of Fourier-Mukai functors for matrix factorizations, right? So given a matrix factorization E in D of x cross y, the superpotential for x, box 1 minus 1 box the superpotential for y, this induces a functor from d of x superpotential, sorry, I need the signs the other way, to d of y, the superpotential for y. So what do you need to do? You need to take a matrix factorization here. You need to pull it up in tensor. And then the hardest part is to push down and to have these sort of things given by finite rank vector bundles remain of the same type. So that I'm really sweeping under the rug. Why the push downs are okay. If you say unbounded quasi-coherent all the time, push downs are no problem. Okay. And moreover, O delta in D of x cross x with the superpotential minus W box 1 minus 1 box W, this induces the identity. So this functor, so phi after psi is induced by O x equals 0 dual box O of x equals 0. Right, this was, right, you had an exercise at some point. If you take a box product, right, so recall from last week's exercises that if I take f box g on x cross y induces the functor from d of x to d of y given by E goes to R gamma of E tensor F tensor G. And so it is with matrix factorizations. So this is how are we doing for time? Doing all right. So we just need to say, we need to say that O x equals 0 dual box O x equals 0 is isomorphic in the derived category of A2 cross A2, whatever the W is, with O of the diagonal. Plus, sorry. And actually, let's relabel. Let's say that, let's call A4 is A2 with coordinates x1 and p, well, how about x and p cross A2 with coordinates y and q. And then we're interested in, I think the way I've set it up, it should actually be minus xp plus yq. Okay, so it's the same as what we did before, but off by a sign. And then this thing you could believe, well, let's see. The matrix factorization for x equals 0 was, was O plus O minus 1 with the matrix D is X and P. Right, we said that OX equals 0 was equivalent to this locally free thing. So the dual is O plus O shifted by 1, where D is just the transpose. And to be perfectly honest, I'm not sure if I want a minus sign there. And I claim that when you sit with all your R charges and everything, that this thing is isomorphic to O of P equals 0. So what we want to say is that on that A4, so on A4, we want that O of P equals Y equals 0. Right, so this one, when we dualized, the X turned into a P. This one, when we dualized, sorry, we didn't dualize that, but we relabeled the X as a Y. We want this to be isomorphic, so not just on A4, but maybe in D of A4 minus XP plus YQ. We want this to be isomorphic to O of P equals Q, right, P equals Q and X equals Y, which is O of the diagonal. All right, so this is two this is two linear spaces in the locus W equals 0 in A4. Two A2s. And we've seen, and we can deform one into another. Right, I just take the family P equals TQ, Y equals TX, and when T equals 0, that'll be that one, and when it's that, it'll be that one. And if I've not made a mistake, that'll be a straight line. We can deform one into another. But we've seen, but X1 of this matrix factorization with itself is 0. So the object of the category of matrix factorizations doesn't deform, doesn't change as we deform, as we go. Okay, if if you are unhappy to just assume that the whole deformation theory works exactly the right way for these objects. So alternatively, you can write down an explicit isomorphism between the matrix factorizations for different different A2s in W equals 0. Actually, okay, so, and there's a subtlety here. There are two families of A2s in here. If you pick two in the same family, you'll get the same matrix factorization. And if you pick one in the other family, if you switch families, as I did here, going from x equals 0 to p equals 0, switched families, then you'll pick up a shift. So if you like Clifford algebras a lot, you can write this down explicitly. Or Ed has suggested you could compute hum from this one to that one and see that it's one-dimensional, and so they're probably the same. Okay. All right, so that was a sketch, at least, of the proof. So the things that I'm sweeping under the rug are how do push forwards work to make Fourier-Mukai all right. That's a big deal. This deformation theory argument is beautiful, but you have to believe in deformation theory, or this argument is totally watertight but messier. And then also I've left it to you to check a bunch of R-charge shifts. So what changes if we're doing, sorry, questions about any details? So what changes if, first of all, we pass from a point in A1 to a divisor in another space, right? Where shall I write it? I'll write it here. If we pass from the point x equals 0 in A1 to the set S equals 0 in some arbitrary x, where S is a section of some line bundle, then, well, we just replace W equals Px with W equals Ps, and we just write exactly all the same equations and everything. You literally just mutatis mutandis. In higher rank vector bundles, well, there was nothing special about quadrics in A4, well, in A2 and A4. You would get the same sort of Koszul resolutions and sort of Cliffordy matrix factorizations from quadrics in AN and A2N. So let me just say, you do linear spaces on quadrics in AN and A2N. And it's the same outcome with more bookkeeping. You know, the Koszul resolution that I started with is longer. It's just a lot more bookkeeping. Or if your thing was a complete intersection, right? If E was a sum of line bundles, you could try to induct. All right. I have 10 minutes to kill. What shall I do with it? So is Ed gone? Is there anything from your lecture that you want me to say in 10 minutes? Or should we just quit? Maybe we'll just quit. Thanks for hanging around for 2 weeks of a very intense program. I'm impressed that so many of you have stuck with it as long as you have. Let me say we do have, at Oregon, we have a bunch of postdoc positions next fall. Sasha and I are not on the committee that reads files, and who knows whether we'll get to hire anybody. But if you're on the market do send one of us an email so that we make sure that your file gets looked at. All right, thanks.